All right. So, welcome to United Astronomy Clubs of New Jersey. I notice a couple of you are still wandering in. We This is our second to last presentation of our not our second to last presentation, our in-person presentation of the year. We are open every Saturday, April through October, as long as weather permitting, since we now hold our lectures outdoors. When we made the call today, the weather was supposed to be a bit more clear this hour. Unfortunately, it is very wet, very misty, and very overcast right now. So, a couple things to note. We are actually live streaming, and we now live stream every presentation onto YouTube. So, if you ever can't get here, if you can't get a reservation, check us out on the YouTube. We and all our past presentations are also on the YouTube. So if you happen to miss it for whatever reason, you can always go back and view. Hit up the comment section if you have any questions. I do periodically check those to try and answer them. So, um, with that being said, uh, United Astronomy Clubs of New Jersey welcomes you. We are a completely nonprofit program, so all of the donations you guys have done throughout the year and past years have helped keep us our lights on, our ability to offer the free public programs because this is completely free to you guys. We only have the reservation system just to kind of, unfortunately, with COVID, still limit audience size. So if you want to check us out and come in person, your best bet is to look at our website, uacnj.org. That's going to give you a whole list of our telescopes we have, our various observatories. It's going to give you information about our member clubs because we are a club made up of other clubs. Uh, as well as that, you can also check us out on our social medias, our Facebook, Instagram, Twitter. We got a Discord server now. And with that, a couple things for our live audience. If you do need to use the restroom, we have the porta potty to my right, your left. It has the red light on it. We also have a gift shop to my left, your right, this door outlined in red. And I'm the one manning it, so you will have to wait till after the Q&A session for me to go in there. But you can check it out in the meantime. And like I said, after the presentation, I'd be happy to help you over there. We do, obviously, it's a bit dark with it being overcast. So if you do need to use lights, we just ask you keep your flashlights and whatnot pointed towards the ground because we like our being able to see. That being said, though, you are going to use your headlights leaving because we also, as much as we like being able to see, we do not like getting run over by cars. Been there, done that, don't suggest it. So, with that, we're going to get going into our program today. I just need to pull up the intro. So, tonight's presentation is A Tale of Two Circles From Orbits to Atoms with Dr. Gary DeLeo. Dr. Gary is an emeritus professor of physics at Lehigh University, where he was employed for 40 years before retiring in 2020. He has served as an associate dean in the College of Arts and Sciences and chair and associate chair of physics. Professor DeLeo's early research was in the field of theoretical solid-state physics, primarily studying atomic imperfections in otherwise perfect semiconductor crystals. His passion for astronomy led to his change in research to astrophysics, where he studied binary stars. For 30 years, Professor DeLeo directed considerable attention to pre-college science outreach and teacher training in science. He has presented about 1,500 science outreach programs since October 2003 and many others prior to that. He loves to share his understanding and appreciation of science and does it with passion, excitement, and laughter, and I can attest to that one. He is the recipient of 7 awards and honors for excellence in teaching and outreach. And with that, here's
Thank you
Gary.
so much. Thank you. Next time, next time I should give you the short version of that. Okay, today I'm going to talk about actually circles, but of two kinds, because they're really. For example, we're going to be talking about things like planets and moons and binary stars that move in circles around a central body. And we'll also deal with the elliptical motion, that because they're not all in a circle, some move in kind of a squash circle. And we also have the electrons that in some sense orbit the atom, another form of circular motion that appears in nature and is studied by scientists. And there are relationships between the two and differences. One of the big differences we see here is in scale. So that, for example, you can see that if this is like one atom size and dimension, the distance between like an electron and a proton in like a hydrogen atom, this is 7 billion times larger. The distance between a proton and its electron is so small that the distance between the Earth and the Moon is 7 billion times larger. So the scales are enormous here, and that makes quite a difference. So let's talk about circular motion. The simplest way to understand something moving in a circle is a balance between two forces. For example, that guy over there hanging on that door is experiencing what we might call centrifugal force, an outward force, as that car is moving around a circular path. But that's balanced by the holding on for dear life force that that the door is actually exerting on his hands. So you see there's a balance between the outward force and the inward force toward the center of the circle. Now, this is one way to deal with the problem, but I can tell you that scientists, physicists don't really like dealing with it that way, because centrifugal force is not really a force. We sometimes call it a fictitious force. In fact, if you try to ask yourself the question, what is the agent that exerts the force, you really can't come up with an answer, because it really isn't a legitimate force in that sense. So what we like to do is use Newton's second law. And by the way, I'm going to ask you not to panic. There's some math here, but I'm going to do all the math for you. And even if you're not interested in the math, there are going to be numbers that come out that are pretty interesting about how big things are and how small things are. One of the most important equations in physics is called Newton's second law, and it's F equals ma. The force on an object equals its mass times acceleration. The force in this situation here, the force in this situation here is the holding on for your dear life force. And that force has to equal the mass of the man, which is a measure of how much stuff he has in him, times the acceleration of the man. That means we're going to have to talk about acceleration. So what does acceleration mean? Well, let's start off by talking about the simplest case of acceleration, when something is moving in a straight line. Acceleration is nothing more than, you put the pedal to the metal, right? And the car takes off and is gaining speed. That's acceleration. It's the rate at which your speed changes with time. For example, if you drop something near the surface of the Earth, its speed increases at a rate of 32 feet per second every second. That's the rate at which an object gains speed when you drop it near the surface of the Earth. So, for example, after the first second, an object starting at rest after the first second is moving at 32 feet per second. But after the second second, it's moving at 64 feet per second, and so on. That's acceleration, and this is a special case of an object accelerating due to gravity near the surface of the Earth. Now, what about things that aren't in a straight line? And here's where it gets a little tricky, because scientists have distinguished between two words that normally mean the same thing: speed and velocity. When we talk about velocity in physics, we're talking about how fast it's moving and in what direction it's moving. And that's really important, because changes in direction are as important as changes in speed when something is moving not in a straight line. So, for example, let me imagine that we've taken a baseball and we've thrown it up into the air, and it's following a ballistic trajectory. It's going, doesn't make that noise really, but right, I like making the noises. So it's following a ballistic trajectory up into the air. And by the way, can you see this okay? Is my laptop in the way? Are you okay with that, everybody? Okay. So anyway, this arrow right here represents the old, or the starting velocity. The length of the arrow is a measure of how fast it's moving, and the direction of the arrow is, well, the direction it's going. Now, at a later point, oh my God, because that screen is rippled, it looks like my ballistic trajectory is like a little weird there, right? But this is actually, you know, following the path you'd expect a baseball to follow. Now, notice a little later, it's going a little slower, right? Doesn't the baseball slow down as it goes up? And it's also changing direction. It's going up at first, and eventually it's going to be coming down in another direction. So the actual velocity is the actual acceleration is the change in velocity, which is actually the change in the arrows. So in fact, you can see that if I go from the tip of the old arrow to the tip of the new arrow, that delta v, that sign there, delta, simply means change. That change in velocity is actually pointing downward. So the change in velocity is pointing straight toward the ground. And that's very interesting and not surprising at all, because remember, force equals mass times acceleration. Whatever direction the force is in, which is down, gravity pulls down, right? The acceleration is in the same direction. So wait a minute, how do we get to acceleration here? Change in velocity is in fact acceleration, right? So the rate at which velocity is changing is acceleration. Let's actually take the circle now. God, that looks like a terrible circle. I drew it better than that, but this screen is really kind of funny, but that's kind of interesting, right? Okay. See, with PowerPoint, you know, you don't have to worry about taking a pencil and trying to draw a circle, which I can't do at all, right? So that's a real circle. So let's imagine something's moving in a circle. It's moving at a speed v. This time I mean a speed, but it is going in that direction. Its mass is m, and the distance from the center of circle is r. So it's moving in a circle of radius r. Now, I know this is a little tricky, but I think you can understand this. I think you can follow this, because it is kind of cool. Like I said, don't panic unless I say panic. Okay? So, originally, let's suppose the object is right here. That's the original position of it, and this is the original velocity. Now, a very short time later, it's now moved over here. So its new position is given by that arrow, and its new velocity is given by that arrow. And I'm going to make triangles with these arrows, because I want to show you something here. Because one thing for sure, whatever angle change that we have going from here to here, whatever angle that is, that's got to be the same as the angle change from there to there. So when I make two triangles out of these, you see I can make a triangle out of this one. Here's the starting velocity. Here's the ending velocity. There's the difference in velocity, the change in velocity, right? But watch when I take this guy right here. That triangle is similar to this one, because that angle there and that angle there have to be exactly the same. So the triangle with two v's and a delta v is similar to the triangle with two r's and a delta r. This is real physics we're doing here, by the way. All that's going to matter in the end is the result, but hopefully you can kind of see how we can get something out of this. Because I can tell you that the ratio of this side to that side of this triangle has got to be the same as the ratio of that side to that side of that triangle, because they're actually similar, because they have the same angles. Now, I can now multiply both sides of this by v. So v over v is just 1, so that disappears, leaving us with the change in velocity on this side. And then it gives us a v over here. And look at this. If I divide both sides by a little period of time, I'm going to get the change in speed divided by the elapsed time. That's nothing more than the acceleration. That's the change in velocity per second, because delta t, the little increment of time, is the per second part of that. So notice now that the change in velocity with respect to time is acceleration. But wait, The change in position with respect to time is nothing more than speed, how fast it's going. Miles per hour, meters per second, distance divided by time. So what we can find is, see, this thing is, that's a v, but that's also a v. So what we can find is that for something moving in a circle of radius r at speed v is nothing more than v squared over r. So the faster you go, the greater the acceleration. The smaller the radius of the circle, the greater the acceleration. So the bigger the thing in the numerator, the greater the acceleration. The smaller the thing in the denominator, the greater the acceleration. So the acceleration of something moving in a circle is v squared over r. So it doesn't really matter whether or not you followed the argument. That is the result for something that's moving in a circle. Now, by the way, the other thing is, did you notice that the change in velocity, which means the acceleration, notice it points toward the center of the circle? So not only do we know the magnitude of the acceleration, v squared over r, we know its direction. It's pointing toward the center of the circle. And that's not surprising, because remember the holding on for dear life force was pulling toward the center of the circle? Acceleration and force have to be in the same direction. So now we can apply this to the orbit. Here's, for example, the Earth moving around the sun. So let's take a look at the Earth moving around the sun. And I'm going to just put in some symbols here. Again, nothing really scary. They're just symbols to represent the different quantities of interest. Let's say capital M is the mass of the sun. Little m is the mass of the Earth. V is the speed of the Earth as it goes around the sun. R is the distance between the sun and the Earth. P is the period, meaning the amount of time it takes to go around the Earth. 1 year, 365 days, whatever units you want. And F with the G is the force due to gravity that the sun exerts on the Earth. This is the thing that's keeping the sun moving in Earth moving in a circle around the sun. Now, you ready for this? Here we go. Remember, F equals ma. Force equals mass times acceleration. But wait! We already found the form of the acceleration for something moving in a circle. It's nothing more than v squared over r. So the acceleration of the Earth as it moves in a circle is v squared over r. So the force due to gravity must be mv squared over r. But what is the force due to gravity? The force due to gravity depends on actually three things. It depends on the mass of the sun that's pulling on the Earth. It depends on the mass of the Earth, the thing being pulled. But it also depends on the distance between them. There's an r squared down here in the denominator, which means if I were to take the Earth and move it twice as far from the sun, the force on the Earth due to the sun would only be 1/4 as great. It'd be 4 times less. So in other words, this F of G, that's the force that goes in here. So G capital M little m over r squared has to equal mv squared over r. Now, watch what I'm going to do here. If I divide both sides by m, the m on the left and the m on the right disappears. If I multiply both sides by r, we lose one of the r's in the denominator on the left, and we're left with one of them on the right. There it is. This tells us how fast a planet will be going as it moves around the sun if the distance from the sun is r and the mass of the sun is capital M. Now notice this. This is very interesting. The speed at which an object moves around the sun at the distance r from the sun doesn't depend on the mass of the object that's orbiting. For example, if I put a little satellite in orbit around the Earth 100 miles up, and I put a big satellite in orbit around the Earth 100 miles up, they both go at exactly the same speed. It only depends on the mass of the thing at the center that's attracting them and causing them to move in a circle. Now let's put some numbers in now, because here's where it gets fun. Because there's the speed, right? That's the speed of a planet the Earth or any other planet as it orbits the sun. Remember that capital M is the mass of the sun. It's always the mass of the thing at the center. And that r is how far the orbiting object is from the thing at the center. Let's put some numbers in. And don't worry about where these numbers came from. Oh, by the way, I forgot to mention this. That capital G is called the gravitational constant. And it's a measure of how strong the force of gravity is. It's about 6.67 times 10 to the minus 11th in units that involve meters, kilograms, and seconds. The mass of the sun is 2 times 10 to the 30th kilograms. And the distance between the Earth and the sun is about 92 million miles, but that translates into 1.5 times 10 to the 11th meters. And by the way, those exponents there simply mean add that many zeros, move the decimal point over that way, that many zeros. If it's negative, it means move the decimal point the opposite way, that many zeros. It's a shorthand notation called exponential notation. But anyway, this tells us that the Earth, as it moves around the sun, moves at a speed of 29,800 meters per second. And no matter how hard they try, no one has been able to help me to have any feeling at all for meters, right? So I've got to work in miles per hour, and it drives people crazy. But this tells us that the Earth is moving around the sun at almost 67,000 miles per hour. That's how fast the Earth moves around the sun. And this is how easy it was to figure that out. We didn't even need to measure it. All we need is a certain set of numbers, the mass of the sun, and how far the Earth is from the sun. And knowing that it moves approximately in a circle, and bingo, we have the number. Oh! But we can also calculate that for the other planets. For example, let me, for the purpose of just this spreadsheet here, let me say that distances are in astronomical units. One astronomical unit is the average distance of the Earth from the sun. Mercury is 0.38 astronomical units from the sun. In other words, it's 38% the distance from the sun to Mercury than it is from the sun to the Earth. The Earth goes around the sun at 66,700 miles an hour, but Mercury goes around the sun at 107,000 miles an hour. Because the closer you are to the sun, the faster the object moves. Because there's an r in the denominator, and the smaller the thing downstairs gets, the bigger the number gets. By the way, we can also come up with another number, by the way, and it's a little bit bigger. It's actually bigger by a factor of the square root of 2, but that doesn't really matter. And that is, how fast would a planet have to be going to actually escape from the sun? Well, obviously, that number is going to be a bigger number than the orbital speed, otherwise it wouldn't be orbiting anymore. The Earth would have to be speeded up to, or something orbiting in the orbit of the Earth would have to be speeded up to 94,000 miles an hour in order to actually never come back into our solar system. Mercury would have to be speeded up to 152,000 miles an hour in order to never come back to the solar system again. By the way, we can add Jupiter and Pluto in there. Notice that Jupiter is about 5 times the distance that the Earth is from the sun, and Pluto is almost 40 times on average the distance between the Earth and the sun. But look at this. The Earth is moving at about 67,000 miles an hour. Jupiter's only moving around the sun at about 29,000 miles an hour. And Pluto's only moving around the sun at about 11,000 miles an hour. The farther out you go, the slower the objects go. Hey, but we can go even farther. I mean, Pluto may be the last planet. Oh, wait a minute, not a planet anymore. Sorry about that. Raise your hand if you think Pluto should still be a planet. Oh, these are old scientists here, I can see, and astronomers, right? You know well, it's a dwarf planet, I know. I know. My sister always yells at me because she says, I really am mad that they made Pluto not a planet anymore. But anyway, before we go on and add some numbers in there, let me actually read to you a little bit from this book by Carl Sagan, right? It starts out, these are the snows of yesteryear, the pristine remains of the origin of the solar system. Way out far, way out past Pluto. This book is about comets. And he says they cruise no faster than a small propeller-driven aircraft, a third of the way to the nearest star. Can you imagine that? The Earth is going around the sun at 67,000 miles an hour. And if you go far enough from the sun, you'll find objects there that will eventually become comets once they're disturbed and falling closer to the sun, that are moving no faster than a small propeller-driven aircraft. Can you believe that? They don't go very fast. Well, let me check that out. I don't know if some of you know Emily, right? Anyone know Emily? From NWJAA? Okay, anyway, she took me up in an airplane, and I took a picture of the airspeed indicator here, and it says 90 miles an hour, okay? So we got to figure this out. How far out do you think from the sun you'd have to go before something is orbiting the sun so slowly it's only going 90 miles an hour? So let's come back and fill this in. Well, how about this? Remember that Carl Sagan's book said 1/3 of the way to the nearest star, right? Well, 1/3 of the way to the nearest star is about 1/3 of the way to Alpha Centauri, which is about 90,000 astronomical units, right? And I calculated the orbital speed for that, and it turns out to be 220 miles per hour. Now, if you tried to bring that little plane to 220 miles an hour, you'd tear its wings off. So, not quite. But then, I got curious. How far do you think you have to go before it's 90 miles an hour? The answer is 8.7 light years, or 550,000 astronomical units, which is 8.7 light years past Alpha Centauri. That's how far you'd have to go so that an object out there orbiting the sun would go as small as a propeller-driven aircraft. But I'm not sure Carl Sagan was exactly wrong, because it turns out that, you see, not everything is in an elliptical orbit, especially the stuff that makes these like long-period comets, the stuff way out there. For example, let's take Comet Neowise. Remember Comet Neowise? Raise your hand if you saw Comet Neowise. No? Oh, come on. It was like, I think it was this spring. All you needed was a pair of binoculars. Yeah. All right, don't worry. We got Halley's Comet coming in, well, whatever 86 plus 76 is. I can't add in my head very well. That's why I use spreadsheets so much. But anyway, it turns out that in a mechanics course that I teach or taught when I was still employed, I actually worked out orbits for ellipses. You see, a circular orbit is a special case of an ellipse. Orbits, you know, basically don't have to be perfect circles. They look like squash circles, and that's a very defined mathematical shape called an ellipse. But it turns out that, believe it or not, if you have a comet or an object in an elliptical orbit, like an asteroid or something, the close distance for the sun is called perihelion, and this is the formula that would tell you how fast it's moving there. The far distance from the sun is called aphelion, and this is the formula that would tell you how fast it's moving there. But, well, notice there are two other symbols in here that we haven't seen before. One of them is A, and one of them is this Greek symbol called epsilon. Well, it turns out that A is basically the semi-major axis. It's half the length of the long dimension of the ellipse. And epsilon is the eccentricity. It's a measure of how much it's squashed, right, from being a circle. So and by the way, eccentricity would be 0 if we were talking about a circle. So if I plug those numbers in as Comet Neowise, if those numbers are right, if those estimated A and epsilon are right, near the sun, it went around at 178,000 miles an hour. But when it reaches its far point over here, it will be going at only 70 miles an hour, and that is even slower than I was moving in that little Cessna airplane. Now, the other thing we can look at is the orbital motion around one of the bodies in our solar system. For example, let's suppose we were in orbit around the Earth. So let's suppose the object with the mass capital M wasn't the sun. Let's suppose it was the Earth, and we're talking about something orbiting the Earth, something like the International Space Station or a telecommunications satellite. To orbit the Earth, and by the way, LEO means low Earth orbit, and by surface, what I mean is that it's orbiting essentially at the surface of the Earth. But you might say, you can't orbit at the surface of the Earth, you'd be inside the atmosphere. Well, if you're orbiting just a couple hundred miles up, believe it or not, for all practical purposes, you're orbiting at the surface of the Earth. Because the Earth's radius is like 4,000 miles, right? And 200 miles above that is hardly any farther from the center, right? So the astronauts that are in orbit, like in the space station, they're basically orbiting at the surface of the Earth because the atmosphere is very, very thin. But to stay in orbit at near the surface of the Earth, it's a speed of roughly 17,700 miles an hour. Escape velocity, you probably have seen that number before, like when the astronauts went to the moon. They had to fire the third stage rocket a second time to speed themselves up to 25,000 miles an hour approximately to leave the gravitational pull of the Earth and actually never fall back down again. For the moon, orbital speed near the surface, and that's called, that LLO would be low lunar orbit, is about 3,800 miles an hour and 5,000 miles an hour to escape. By the way, if you wanted to go into orbit around Jupiter, you'd be moving at a speed of 94,000 miles an hour. So the spaceships, if they were in orbit close to the cloud layer, it would be 94,000 miles an hour, a little less higher up. And to escape Jupiter from its cloud layer, you'd have to move at 133,000 miles an hour to escape. Now, you want to see something really weird? Look at this. Look at the moons of Mars, Phobos and Deimos. Let's take a look at escape velocities. On Deimos, the escape velocity is only 15 miles an hour. So if you bent down and jumped, you would never fall back down again. A good hard jump on Phobos, on Deimos rather, and you will not fall back down. By the way, to go into orbit, you'd only have to pick up a speed of 10 miles an hour. So maybe a hard push off your legs horizontally, and you could be flying like Superman all the way around the moon. And on a place like Icarus, like an asteroid, its escape velocity is 1 mile an hour. In fact, you'd have a hard time keeping yourself on the ground on Icarus. So these are kind of the ranges. We've got Icarus, escape velocity is about 1 mile an hour. Jupiter's escape velocity is about 133,000 miles an hour, and the Earth is about 25,000 miles an hour. And we can get all this by a little bit of arithmetic that comes from F equals ma, force equal mass times acceleration, which is Fig Newton's second law. That was a joke. His name isn't really Fig. It's Isaac. Okay. You can laugh, too. I know it's dark, right? You see, I can't see when you're smiling, so it's really hard to tell. All right. Now, let me tell you something else interesting, because this was discovered, Kepler's third law, before Newton even came up with his equations, because Kepler recognized something really weird. He said, you know what? If I take the radius of the planet's orbit, right, r, and multiply it by itself 3 times, and then I take how long it takes to go around the sun and multiply it by itself 2 times, you know what he found? He gets the same number for all the planets in the solar system. He gets a constant. He does it for Mercury, and he does it for Jupiter, he does it for Saturn and Mars. He gets the same number every time. Let's try it. I'm going to try it right here. Here is the distance in meters between Mercury and the Sun. There's the time it takes in seconds for Mercury to go around the Sun. I'm going to multiply that by itself again, and that by itself one more time. And then I'm going to divide by this and then divide by that again, and I get this number right here. And remember that 18 simply means move the decimal point to the right 18 times, 18 places. But watch this. If I do the same thing for Earth, look at how different all these numbers are. Mercury's very close to the Sun. Jupiter's far from the Sun. Mercury takes a very little amount of time to go around the Sun, but Jupiter takes a long time to go around the Sun, and yet I take these very different numbers, and notice that I get approximately the same number every time. This is what Kepler found before Newton even came along. And by the way, for Mercury, Earth, and Jupiter, the object at the center for all three of those is the Sun, right? Mercury orbits the Sun, the Earth orbits the Sun, Jupiter orbits the Sun. Let's take a look at another set of three objects that all orbit the same body, but they orbit a different body, not the Sun. Io, Europa, and Ganymedes are all moons of Jupiter, right? So they all orbit, they're all different, they all orbit the same object. This is how far each of them is from Jupiter. This is how long in seconds it takes for each to go around, and look at this. Do you notice you get exactly the same number every time? It's not the same number we got for the Sun, but it is the same number for anything orbiting Jupiter. It gives you the same number. Now, Kepler, how did he figure this out? Trial and error. He just noticed that if he mixed and matched the numbers this way, he would get a constant for the planets. He didn't yet know about this yet. I mean, we had to wait for Galileo to come along and Amos. Although, you know, I'm not quite sure of the timing there. I'm not sure he knew about the moons of Jupiter. I don't think he did. But now, I am going to prove to you that what you just learned using Newton's second law actually predicts that r cubed over the period squared will be a constant, because it will only depend on the mass of the thing about which those objects are circling and nothing else. You ready for this? You ready? Remember, force, this is the force of gravity, equals mass times, remember, the acceleration of something moving in a circle is v squared over r. We'll cancel the m's, which means little m's, which means we're just dividing both sides by m, and m over m is just 1. 5 over 5 is 1. 7 over 7 over 1. Anything over itself is 1. And then, what about the speed? Well, what's the speed of an object moving in a circle? Isn't speed how far something goes divided by how long it takes to go that far? Right? Miles per hour, right? Well, how far does the Earth go, or a planet go, when it orbits the Sun? It goes around whatever distance the circumference of a circle is. But remember, the circumference of a circle is 2 pi times the radius from your math classes. So the distance it has to travel is 2 pi times the radius. And how long does it take to go that far? Well, we call that the period, because the period is defined as how long it takes to go around once. So I am going to stick this guy in here, right where that V is. And I'm then going to do a little bit of manipulation. And I'm going to solve for m, which I put in green, the mass of the Sun. And notice that the mass is 4 pi squared g over r cubed over p squared. Now look at this. 4 is a constant. That's just a number. That doesn't change. Pi is a constant. That's a number. It doesn't change. G is a constant. It's a number that's a measure of the strength of gravity. That doesn't change. What do you end up with? R cubed over p squared. So r cubed over p squared only depends on the mass of the guy at the center. It doesn't depend on the mass of the planets, where they are in relationship to the Sun, or how long it takes to go around. But even though r is different for every planet and p is different for every planet, r cubed over p squared only depends on the mass of the Sun, and the mass of the Sun is the same for every planet, because there's only one Sun at the center. And Newton was able to demonstrate why Kepler's third law worked the way it did. And that is really pretty amazing. So, and by the way, this gives us some other information. If we know the period and we know the distance, we know the mass of the sun. If we know the period of an object and how far it is from the thing it's orbiting, we can find the mass of the thing at the center about which it's orbiting. And I'm going to see if we can find the mass of the sun. You ready? Let's try it out. Okay? Let's see if we can do this. Here's 4. There's pi is 3.14 squared. Here's r cubed, the distance from the Earth to the sun. Here's the gravitational constant. The period of the Earth. Well, how long does it take the Earth to go around the sun if I put it in seconds? Well, it's 365 days times 24 hours in a day times 60 minutes in a second times 60 minutes in an hour times 60 seconds in a minute. And then square that. The mass of the sun is 2 with 30 zeros after it kilograms. But the beauty of this is not just that we can to the sun. We can measure the mass of anything about which a smaller object is orbiting. For example, when we finally discovered the moons of the moons of Mars, we immediately knew the mass of Mars because you could figure out how far each moon is from the center of Mars, and you can measure how long it takes to go around once. So you can measure that, multiply it by that guy, that gives you the mass of the thing at the center. So suddenly, as soon as we found Phobos and Deimos, we had a very good measure of the mass of the sun. And another thing we can use it for is binary stars. In other words, how do we know the masses of stars? The answer has to do with the fact that as long as we have one star orbiting another, we can actually learn something that we could not know firsthand in any other way. As long as there are so many stars that are double stars, which there are, right, then we can figure out the mass of a star. Now, let me point out something else. This is a little complicated. That equation is only correct if the little guy orbiting the big guy is really, really small compared to the big guy. You see, this equation is not quite correct. Let's suppose there's the mass of the central object and there's the mass of the object orbiting. Maybe this is the Earth and that's the moon. Or maybe that's a red star and that's a little blue star orbiting it, right? Okay, or a big blue star. As long as the mass of this guy here is insignificant, that's correct. But you want to know what the real formula is? You're not actually, with that equation, measuring the mass at the thing of the center. You're measuring the sum of the two masses. Uh-oh. Now, like I said, if the thing orbiting the big guy is small, like the mass of the Earth is very small compared to the mass of the sun, almost insignificant. The mass of the Earth is almost 0 compared to the mass of the sun, so it's as if that guy isn't even there, and it looks like that. But let's suppose you have the Earth and the moon. That wouldn't work out quite right, because the moon is a small fraction of the mass of the Earth, but it's still significant. And let's suppose you have two stars where they're almost the same mass. All this equation is going to give you is not the mass of that one or that one. It's only going to give you the sum of the two masses. So how do we deal with that? How do we deal with that? Well, here's how we deal with it. Let's take an example. We knew for a long time that Sirius, the star, had a companion that was orbiting it because we could track the motion of Sirius, and as it moved slowly across the sky, and it wasn't a straight line. What we discovered was that there was another star. We could predict its presence, and it would be following the path of that dotted line in the sky. And eventually, you see with the Hubble Space Telescope, there it is right there. It's a white dwarf. There is a star pulling on Sirius A. Okay? So the thing is, by using this information, the information given here, and this information, we have enough information to separately determine the masses of the two. For example, you see, the R that's there is actually R1 plus R2, the distance from the center of the circle about which both are revolving, right, of one object, and R2 is the same for the other object. So what we have, in mathematics, we'd say we have two equations and two unknowns, and as long as we have that, we can solve for both. So in other words, this gives us, using this here, we can get the sum of the two masses. But then using this ratio, we can find the ratio of the two masses, and using that, we can figure out individually what the masses are. Now, we're talking about stars now, so let's talk a little bit more about them. How hot are they? How far away? How bright? How big? Well, that's actually the subject of a different talk altogether. That would be like a whole another hour or more. But their masses, by the way, look, see the smiley, happy face, sun smiley face there? We actually figured that out. So we figured out how we can find the masses of stars. But what about what they're made of? What is their composition? And that would involve, what are the atoms that make up the stars? What is the atomic structure of the stars? Let me not go into detail about the structure of the stars, but let me say this. You probably have heard the word spectroscopy, and you probably know that the light from a star can tell you what it's made of. And I'm going to show you how that is, how the light from a star can tell you what it's made of. Let me just get back here again. You see, the surface of the star, if we forget about its atmosphere, is a glowing hot object. It's called a black body because, like, if you took like a black bowling ball and you heated it up, it would glow with a spectrum, a rainbow of colors that basically would provide you with an information about how hot it is. But it's a continuous distribution of colors from red to violet. But remember, the light from a star actually has, or the sun, has to pass through its own atmosphere. And when that light passes through its own atmosphere, we actually find that it isn't just a continuous distribution of colors from red to violet. There are dark lines in there. Those dark lines, it turns out, is a fingerprint of the types of atoms that make up the star. And I want to describe to you, by using circles again, how that fingerprint comes about. Okay? Now, by the way, first of all, I want to point out that as a consequence of gravity, we can have one object orbit another because gravity is attractive, right? But gravity isn't the only attractive force that appears in nature. We also have the electrostatic force. And the electrostatic force, this is somehow not going to let me do this, and I don't know why. Okay? Oh, here it is. Oh, it's going. It's working. Do we have sound, by the way, or not? Okay, doesn't matter. I'll describe it. This thing here is a little electrostatic, a little rod in orbit in the space station. And the astronaut's going to rub it with a piece of paper. We don't need we can need the audio. I got it. I'm fine. Now it's fine, really, because you say I'm going to explain it. He charged it by rubbing it with a piece of paper. And now he's going to take little drops of water and watch the little drops of water go into orbit around that. You see, they're attracted by the electrostatic force, just like the Earth is attracted to the sun by the gravitational force. So you see, you can have orbits due to electricity, just like you can have orbits due to gravity. And this is how an atom works. And here's where we're going to find our circles again. Okay? Because, by the way, the simplest atom is hydrogen, and that's the atom that is most dominant in the sun and in stars. This time, what we're going to do is, instead of imagining that we have the sun at the center and a planet orbiting the sun, now we have a proton at the center, an electron orbiting the proton. And instead of the force being the force due to gravity, now the force is the force due to electricity. It's almost the same as the force due to gravity. Notice it depends on r squared in the denominator, which means if you go twice as far away, the force is 1 over 2 squared, or 1 over 4, or only 1/4 as big. So now we can do the F equals ma thing for something moving in a circle, but instead of putting in for F the force due to gravity, we put in for F the force due to the electrostatic attraction of two oppositely charged objects, the proton and the electron. When we do that, we can actually find an expression that would give us the speed of an electron. So what is the speed of an electron as it orbits the atom? Well, for the smallest orbit of an electron in a hydrogen atom, and by the way, I'll come back and define what I mean by smallest orbit in a little while. For the smallest orbit, the speed is 4,900,000 miles per hour, which means it's actually going at 0.7% or 0.007 the speed of light. It's going less than 1% of the speed of light, which is still very fast, but still well below the speed of light. But what do I mean by the smallest orbit? Why should an orbit have something that I call smallest? I mean, I can put an object in orbit around the Earth at 100 miles, at 200 miles, or at any distance in between. Why is there a smallest? This is really important because you see, what I've been using so far is called classical physics, and because of the differences in scales, what works on the large scale begins to fail on the small scale. You see, why, if I take a gas, like of hydrogen gas, and I put it in a tube, and I put electricity through it, why instead of glowing all different colors, why do I see like a red and a blue and a violet? Why do I see well-defined colors? Always the same, well-defined colors. It's like a fingerprint for the element hydrogen, right? In fact, like I said, if you shine sun from the light through a prism, you actually find dark spots. Now, by the way, it is not a coincidence that where before I drew bright colored spots, it's not a coincidence that when I'm looking at the light from the sun, I am now drawing dark spots in an otherwise continuous rainbow in exactly the same spots at exactly the same colors. That is not a coincidence. And to understand that, we need to take a look at the atoms. By the way, even though classical physics, these orbits, don't really work for atoms, they actually do. They're still useful vehicles to help us understand them. In fact, the Atomic Energy Commission, which used to exist, had a symbol that looked like that. You see the electrons moving around the nucleus of an atom? This is called the planetary model of the atom. So here's the Earth orbiting the sun, and here is one of the electrons orbiting the nucleus of an atom. And it's not surprising that that model is somewhat true, because we just saw how electricity, the attraction between oppositely charged objects, can pull them together and produce orbits just like gravity with planets orbiting the sun and so forth. Now, scientists attempted to also apply their classical physics to the colors that they would get when you make something hot so that it glows. It failed. It failed miserably. Around the turn of the century, that is the last one, when we came into the 1900s, everything seemed to be going wrong. All these theories that work so perfectly for everything macroscopic seemed to be failing miserably when it depended on things that were happening on tiny scales, such as the scales of atoms. Well, here's another failure. You notice that electrons go back and forth, like, for example, if you have a walkie-talkie, the electrons go back and forth, right? And that sends radio waves out that are picked up by another walkie-talkie. So in other words, when something emits electromagnetic radiation, it gives up energy. I mean, doesn't a walkie-talkie require a battery, right? You need a power source because you're giving off energy in the form of electromagnetic radiation. But get this, once they actually looked at the atom in this picture and said, okay, if we had electrons moving around the nucleus, right, what would happen is that they discovered when they did the calculation that the electron would give up its energy so fast by giving off light, electromagnetic radiation, that the electron would spiral into the nucleus in 1/1000th of a second. That means the universe would be gone in 1/1000th of a second, like gone. But we know that doesn't happen, right? So there had to be something wrong. There has to be something in nature that restricts motion in a way that is not built into any of the classical physics that explains baseballs and planets. And this new theory was called quantum mechanics. You see, classical mechanics works for big stuff but not small stuff. But quantum mechanics seems to work for everything. And it even reduces to classical mechanics when you make the object big enough. Quantum mechanics imposes restrictions. For example, you can buy something for 26 cents, but you can't buy something for 25.5 cents. And when you're on a ladder, you can stand on that step, you can stand on that step, but you can't stand on a step in between, right? Quantum mechanics, like ladders, places restrictions on where you can be, how high up you can be, or what your energy is. Because your energy depends on whether you're in a small orbit or a big orbit as the electron orbits the nucleus. And by the way, when you jump from one rung to someplace lower, you give off energy. If you jump from a rung down to the ground where the rung is low, it gives you just like a little bang. But if you jump from a high rung down low, you get a bigger bang. You get more energy. So the farther you come down, the more energy you give off. And these we call energy levels. So the steps of the ladder are like energy levels. High energy when you're up high, low energy when you're low. You fall off the first step, you go ouch. You fall off the fifth step, you go to the hospital, right? That's what this is. You see, we found out that electrons can only orbit in certain places. Nature has placed a restriction on how they can orbit. And the orbits that are close to the nucleus have a lower energy than the orbits that are farther from the nucleus. And when the electrons, and the other way, real hydrogen atom energy levels look kind of like that. They get closer together as you go higher. What you find is that if an electron drops from that orbit to that orbit, it emits red light. If it drops from that orbit to that orbit, it gives off blue light, because blue light has higher energy than red light. By the way, if you go too high in energy, like ultraviolet, you see, if you went from there to the lowest energy level, you get ultraviolet. And by the way, you know ultraviolet's a higher energy because that would give you sunburn or even skin cancer, right? That's dangerous. X-rays get even more dangerous and so forth. So what happens is, with an atom, the red light is given off when little jumps are made, little drops, and blue light is given off when big drops are made. So watch this. Pew! By the way, you had to imagine the sound of a photon torpedo from Star Trek, okay? So what happens is, when the electron drops from here to here, it gives off red light, okay? But why do we sometimes have dark lines in an otherwise continuous rainbow of colors, okay? So here's what you get when you just excite gases. But what happens when we actually shine light through a gas? Ready for this? Watch what happens. Boom! The electron gets knocked up to a higher orbit, and that particular color doesn't get through. And that's why you have a dark line in an otherwise continuous spectrum at exactly the same place. So when you look at the sun and the stars, you see black lines where the light from the glowing surface of the star beneath the atmosphere couldn't get through because it got absorbed. And it got absorbed by providing energy to an electron that was here and making it jump up to a higher orbit. In fact, you'll even notice that all different colored stars, different types of stars have different temperatures. And here's one of the hydrogen lines right there, by the way. Notice that hydrogen is most predominant, like not in the coolest stars and not in the hottest stars, but the in-between stars. Because when the stars are too cool, we don't have electrons up in the second orbit that can be knocked up to the third orbit. And when stars are too hot, the electrons aren't even there. They're ionized and they're gone. And this can be predicted exactly by quantum mechanics. Now, one last thing I'll mention is that even for atoms, even though the electron is 2,000 times less massive than the nucleus, if we don't take account of the fact that like Kepler's third law is little m plus capital M, we'll get an error which seems small, like 0.05%. But if we correct for the mass, we'll come up with 0.001% error. And then if we add in some other correction terms, our theories, our equations can predict the energy levels of a hydrogen atom to within 0.0000003%. And with that, I'd really like to thank you for coming on this kind of chilly and damp and dismal night. Thank you very much.
All right. Thank you, Gary, for a wonderful presentation as usual. So now what's going to happen is we're going to have a Q&A session. I did notice a couple people, I think, came in during the presentation, so I'm just going to go over brief safety briefing for you guys here. Again, if you need to use the bathroom, it's the porta potty with the red light on it. We do have the gift shop available after the Q&A. I will be hopping over there to run that. When you leave, please use your headlights. We don't like getting run over, and we are sure you feel the same way. We don't have that morbid of a sense of humor here. On that note, if you do have a flashlight or whatnot to help you walk around, do keep it pointed towards the ground because we don't need to add too much extra light flashing in people's eyes possibly. After the Q&A session, there will also be since it's still very overcast, there will be a slideshow behind me of pictures we have taken on previous nights when it has been clear. And I believe, although we don't have observatories open for the telescopes since it's still quite damp, with the roofs open, we will have a couple doors open so you can kind of look in and see what an observatory here and how a telescope would be set up. So, how question and answer is going to work. I'm going to start us off with an online question. I'm going to read it out, and we're going to get an answer, and then I'm going to go to you, and you're going to hold your hand up and wave it about so I can see you, and I'm going to bring you the mic so our online audience can also hear, because chances are if you have a question, they also have a similar question. And with that, let's get started. The first question is, there's been all this talk about circles and how they're so important and everywhere. Another important shape found commonly in nature is a hexagon. Does the hexagon have any importance or pattern that is seen in astronomy?
Okay, I don't think so. I can't be sure. It's possible that there might be some arrangement of objects that could move around each other in some kind of shape like that. But the thing is, it would take initial conditions that are so precise to get anything to move that way that I tend to doubt it's something that we'll find in nature.
All right. And with that, is there a question from our audience here? Oh, hold on. Let me bring the mic out so our online audience can hear you.
And your speaker can hear.
Yeah.
Okay. So when we were talking about objects that were very far away from the sun moving at 90 miles per hour, I was thinking, do you find it likely that there are actually any objects that are orbiting the sun moving at that distance, at that speed, or would they be attracted by something else?
Well, that's a good question. The circular orbit, we had to go way out past Alpha Centauri to find a speed of like 90 miles per hour. So out there, yeah, they're going to be so disturbed by other things that I doubt they're ever going to play any role in our solar system. However, the elliptical orbit would allow something to be moving much more slowly at a considerably closer distance to the sun, and therefore could be disturbed by a passing star and fall into our solar system. And I think that's what Carl Sagan was getting at in his book, that we could disturb things. But the thing is, that speed, the speed of a small plane, would really require it to be the far end, aphelion, for an object in a highly elliptical orbit, which would not be terribly surprising.
All right. Was there another question from our live audience? If there's no question from our live audience, I actually have a question. What are you going to dress up as for Halloween?
It's interesting. Last year I tried to do Halloween in a very safe way with a table which had instructions for the kids to take like this set or this set or this set, right? Nobody understood. Even I emailed a picture to my daughter and she said, "Dad, I don't even understand those instructions." So how I'm going to handle Halloween is something I probably need to think about. As far as a disguise, I think this is bad enough, right? I scare the kids anyway. So probably no disguise, but a more conventional Halloween greeting with candy.
I know last year, close to Halloween, it didn't fall quite on the Saturday, but what I did was I had the candy in little baggies,
Yep.
and then I said, "It's trick or yeet. Now you get to catch."
I like that. That's a little safer. Yeah. Yep.
But if you do happen to attend our program next Saturday, I'm going to be in costume, and feel free if you guys come up to also join us in being in costume, because why not? It's fun.
Can they dress up as aliens?
Sure, why not?
Yeah.
I know Ken generally really enjoys having fellow aliens to converse with.
Perfect. Perfect.
All right. Oh, are you raising your hand? All right. Let me bring you over the mic.
I have a question. So, can a star turn into a planet?
No, except eventually they would cool down. I mean, once a star is a white dwarf, it'll glow for a very long time. But eventually it will cool and harden into something that I don't know that you'd call a planet, but it would be a structure of something, you know. But I don't really know what you call that. People don't talk about it very much.
I'm sure uh, I don't know what age you are because it's very dark and my eyesight is not that good in the dark. But it's possibly if you get into like grad school or whatnot and start needing a thesis, it's something you probably should look into. You know, where there's always going to be more science in STEM fields and things we're going to need to find out and things that and tech that will need to be invented to find those things out. So. Right. It looks like I'm kind of out of questions online. Oh, oh,
So the speeds of the electrons that are orbiting, are those also subject then to the radius distance? So as they move to different stages, they orbit at different velocities?
Yes, they do. They orbit at I didn't hear the first word you said. You said electrons. Do they orbit at different velocities? Yes, they do in different orbits. Yep. Except once you get to quantum mechanics, you have to be very careful about defining things like trajectories. You know, the best way to actually look at an electron is like a cloud of probability. With that cloud, with the different values of probability, determine how likely it would be that a measurement would determine that the electron is at that spot. So it becomes very difficult to actually even call them orbits, but it has a value in being able to talk about it. But trajectories are a little fuzzy when you get to things on the scales of electrons and atoms. But yeah, we can still talk about velocities. Yeah.
all right. Were there any other questions? Nope. Bueller? Bueller? I got at least a couple chuckles this time. So at least one person has seen it. All right. So, since it looks like the questions for tonight have dried up, I want to thank you guys for coming out. I want to thank you, Gary, for giving us a wonderful presentation. I also want to thank our online audience because you guys are the reason we are here, and you guys have helped us greatly and kept our ability to keep offering these public programs. Like you said, do check us out on our website, uacnj.org. It'll have a list of our last talk of the season. It'll have a list of our winter talks as they become available. And also, it'll have, like I said, information on our member clubs and various activities you can do with kids. Um, you also check us out on our social media, our Facebook, Instagram, Twitter. We also have like I said, the Discord chat. If you are into that, where if you have questions on your telescopes or astrophotography, that's gonna be your place to go, and I can get you answers for those questions. Um, with that, thank you and have a good night.